Elle a auparavant effectué une thèse sur la formation et l'évolution des amas de galaxies à Tel Aviv. Et elle a donc obtenu un premier postdoc à l'IAP dans le cadre d'un contrat ERC qui était piloté par Jossilk, puis un autre contrat dans le cadre du LABEX Institut Lagrange de Paris, et enfin dans le cadre d'un projet émergence de Sorbonne Université, et ça toujours à l'IAP. Ensuite, elle est partie à Potsdam, à l'Institut Max Planck de physique gravitationnelle, dit l'Institut Einstein, et puis pour revenir enfin à l'IAP comme maître de conférence. Alors, ses activités de recherche sont fort riches et elles s'inscrivent vraiment dans un contexte largement interdisciplinaire. Elle a travaillé en effet avec de nombreuses personnes, des physiciens, des astrophysiciens à l'IAP et ailleurs. Alors, je ne vais pas tout citer, hein, mais il y en a vraiment beaucoup. Jossilk, Patrick Petitjean, Paz Beniami, Stéphane Gorielli, Johan Dubois, Jean-Philippe Uzan, Cyril Pitrou, Enrico Barros, Martha Volontéry, Frédéric Daigne et moi-même. Donc, beaucoup de monde, et puis je n'ai pas cité tout le monde. Elle a construit des modèles numériques qui reproduisent l'évolution des galaxies à travers les temps cosmiques, et cela dans le cadre de la formation hiérarchique des structures, tout en suivant conjointement la nucléosynthèse stellaire, l'évolution chimique du gaz dans ces structures, ainsi, comme on le verra après, les taux d'étoiles massives, des trous noirs et des étoiles à neutrons. Elle s'intéresse en particulier au taux de coalescence des objets compacts et de leurs propriétés afférentes, ainsi que les fonds d'ondes gravitationnelles associés à ces structures. Elle étudie enfin tous ces processus physiques en regard des expériences sur les ondes gravitationnelles, excusez-moi, LIGO, Virgo et LISA, future LISA. Je peux dire qu'elle est désormais aujourd'hui experte dans cette nouvelle discipline qu'est l'astronomie des ondes gravitationnelles. Alors, Irina a déjà obtenu, malgré son jeune âge, plusieurs récompenses. Par exemple, les prix qui avaient été alloués par la Fondation Gatti pour la meilleure enseignante et pour ses travaux de recherche entre 2012 et 2014. Elle est aussi membre du comité d'allocation de temps d'observation pour le télescope spatial. Et très récemment, il y a 10 jours, un projet CNRS franco-belge qu'on appelle IRP, International Research Project, vient d'être sélectionné. Donc, ce projet international portera sur l'origine des éléments lourds dans l'univers, objets compacts bien entendu et nucléosynthèse associée. Et ce projet va démarrer dès 2021 pour 5 années normalement. Et Irina donc, sera le pilote de ce projet franco-belge. Alors voilà, j'ai donc le grand plaisir de donner la parole à Irina, qui va parler aujourd'hui de l'évolution cosmique des trous noirs et autres étoiles à neutrons et de la nouvelle astronomie gravitationnelle. Irina, tu as la parole.
Bon, merci beaucoup Elisabeth pour cette présentation. Okay, I'm going to switch to English. So thank you very much for this presentation and for inviting me. It's a great pleasure to be talking at the IP seminar, although I would have much preferred to do it in person. It feels really a bit weird to do it over Zoom. So I'm going just to start. As Elizabeth mentioned, the work I'm going to show and previous works I've done with collaboration with many people, including many people in IP, as well as some people in the Virgo collaboration with the consortium. So I'm going to start with this cartoon that everybody I think saw that shows the recent discoveries of gravitational wave by gravitational wave detectors, LIGO and Virgo. So in blue, we have the binary black holes, and in red, the binary neutron stars. And obviously this, as we know, these discoveries completely change this field and by bringing new and unexpected information. For example, the masses of a lot of these these black holes are much larger than what we expected by just looking at our galaxy. And in some cases, they are really surprising, like this very recent discovery of an intermediate mass black hole. Like the total mass of the merger is over 150 solar masses. There are extremely light black holes as well that were detected. An extremely massive neutron star that was observed, and the possibility of a binary of a neutron star black hole binary. And all these detections opened a lot of possibilities for studying the populations of these objects and to explore the formation scenarios in connection with stellar evolution models. So to go a bit further, what can we expect in the future, and what is the landscape of future discoveries of binary complex object mergers? So in this plot shows the horizon distance, or the maximal redshift of detection as a function of the total mass of the binary in the source frame. So here you see the design sensitivity in red of LIGO, Virgo, and Kagura, the Japanese instrument. And you can see that it peaks at around redshift of 2 for a total mass of about 100. So that means, let's say, 250 solar mass black holes. And it doesn't go beyond redshift of 2. And if you go to slower masses, that's even, you cannot see even that far away, although redshift 2 is, of course, very impressive as it is. But for binary neutron stars, you can only observe them really in the very local universe. Of course, this will be improved with the future generations, like the LIGO Plus and the Voyager, that will improve the current detectors, and future instruments like the Einstein telescopes and cosmic explorers that will really go to extremely high redshifts for a large range of stellar mass black holes and also binary neutron stars. But in the meantime, can we study these mergers kind of indirectly? What can we say about these mergers that occur at higher redshifts, possibly in very different environments than our local universe? And can we learn from the merger rate that is measured in the local universe and with the gravitational instruments that we have? And what can we learn about these compact objects? So as a first application, I'm going to talk about a few of different ideas in this direction, and some directions that we explored in the last recently in the last year or so. So I want to start by recapping the exciting BNS merger GW170817, which is the first and so far only detection of an electromagnetic counterpart to a gravitational wave event. So the upper plots show the gravitational wave signal, the frequency over time in both Livingston and Hanford detectors, and you see the typical chirp signal. And also this signal isn't lasted for such a long time. You see tens of seconds. It allowed for a very high precision of the gravitational waveform measurement. And moreover, it was, as also you know, followed up by a huge number even of telescopes, both terrestrial and in space. And it showed for the first time a direct association of the binary star merger, a short gamma ray burst, and a kilonova. So in this plot, in the right bottom part of the slide, I show one such example of the many follow-up of the many observations that were performed. And these observations show the spectrum of here the spectrum and the light curve of a typical kilonova light curve. So this was the first direct proof that kilonovae actually are associated to a binary star merger. So what is a kilonova? I'll talk about it a little bit more on the next slide. But the kilonova is produced when the merger in the dense ejecta of the merger, you produce radioactive, you produce heavy elements, which then decay radioactively. They heat this material that is ejected, and the material then emits thermally. And as it expands, it cools. So you see that this light curve shifts toward the more red wavelengths, as is expected from the theory. And in fact, this observation was in most respects very much consistent with the predictions that were made earlier about kilonova physics, and that was very spectacular. And they could infer also the total mass of this heavy elements that were synthesized, which a few % of the solar mass. There was also these observations on the very right show the spectrum of this event, and you can see some hints, some absorption lines that are maybe related to the specific elements these R-process elements that are produced in the ejecta, although it's not clear that these particular observations are very convincing. But nevertheless, as a whole, this was a convincing demonstration that kilonovae are associated with BNS mergers, and they produce exactly the type of light curve that we expected. So a bit small recap of R process elements and kilonovae. So R process elements are basically, okay, so all of the elements heavier than iron are produced through neutron capture processes, and about half of those elements are produced in sort of so-called rapid neutron capture process, which means that the neutron capture is more rapid than the beta decay. And this requires extremely high neutron density, so it has to occur in astrophysical sites. And possible sites where it could occur are compact binary mergers, pi neutron stars and black hole neutron star mergers, and collapsars. And this process can produce both stable and unstable elements. Some of them are observed on Earth, obviously. And so if we look into this production of R process elements by compact binary mergers, then as I said before, the merger takes place in the center here, and the R process elements are synthesized in the ejecta of the merger. The ejecta is then heated and produces this transient optical to IR transient that is powered by this radioactive decay. The rate of this mergers is expected to be very low, about 1% of the core collapse supernova rate. I think it's safe to say that we now know that binary star mergers do produce R process elements. The question is now, are all R process elements produced in binary neutron star mergers? So the other direction of this process. It's not entirely clear at this point. One key thing to remember is that since binary neutron stars, when they're just first created, it actually can take them a lot of time to merge. So once you have a binary, it's typically created with large separation. And it can take a large time. I'm talking about hundreds of mega years or giga years between the formation of the binary and the merger. And nevertheless, this scenario, of course, was explored in many works. So where do we find these R process elements? Of course, we can find some of them here on Earth. We have uranium, we have gold, etc. But we can also observe them in astrophysical environments. So this plot show the abundances of the element europium relative to iron on the y-axis and the metallicity on the x-axis. So 0 means solar values. So the left-hand side plot shows the abundances in the Milky Way, and the right-hand side plots show the abundances that were discovered in the Reticulum 2 dwarf galaxy in the red points. So one thing to notice here is that even in very low metallicity environments, so that means that, for example, in this scale -3, that means 1,000th of the solar iron abundance. So that means that very early on, something that happened very early on in the evolution of the Milky Way here, or this dwarf galaxy on the right-hand side plot, you already have stars. So each point here is a star that is very much enriched in europium. For example, in this point, that means it's 100 times more abundant in europium over iron than the sun. That means that there was some very early enrichment by this R process element europium. Another thing you can see, there's a very large scatter at a given metallicity. And if we look at metallicity a little bit like the time, that means that at certain time, there's a huge dispersion that you could have over about 2 orders of magnitude dispersion at a given metallicity of a given cosmic time. That hints that tells us that the process that is responsible for this enrichment has to be a very rare process. So their binary star mergers actually fit the bill. And in fact, there are several lines of evidence for the fact that BNS binary star mergers are the dominant R process element source. So there have been many works on this subject, and by Elizabeth here and collaborators and others. Here I show a plot from Hotokizaki et al. That show that there are really several lines of evidence that all converge to this conclusion. So, for example, you can and this plot shows the merger rate of the source, let's say unknown source of R process elements on the y-axis, and then the x-axis, the mass produced in R process elements by each event. So obviously, if you want to create the total mass observed in the Milky Way, for example, you either have a lot of events, but each produces very small amount of R process elements, or you have very rare events, but each produces a lot of R process elements. So this constraint is shown basically by this green line here. And then if you overplot the constraint we have from GW 170817 with the local estimate of the local merger rate from just this one event, and the estimate on the mass produced, which you can infer from the kilonova light curve, it sort of falls close to the line that you expect by measuring the total mass in the galaxy. There are other lines of evidence. For example, since again this event proved that BNS mergers are associated with short gamma ray burst, you can measure the rate of short gamma ray burst, of cosmic short gamma ray burst independently, and this range is shown here by these red lines. And it kind of falls again on the, well, you can find this intersection here. It's sort of also consistent with what you find from the previous arguments. You can also measure the abundance of radioactive R process elements, here plutonium, which in some sense breaks the degeneracy, because you also need to account for the half-life time. Especially, you can measure the abundance in early solar systems through the what you measure in the meteorites, and in more recent solar system environments. And it all kind of converges to the same point, including the abundance seen in dwarf galaxies. For example, the galaxy that I showed you just before, the Reticulum 2, there are actually just 2 dwarf galaxies where you measure this overabundance. So it kind of converges towards the same point. So you are tempted to conclude that indeed our binary stars are the source of all the R process elements in the universe. However, when you try to build a complete galaxy evolution model to account for to model this, there are difficulties, and then there is a whole other bunch of studies that come to a conflicting conclusion. And the reason is that if you want to reproduce the observations, so let me just go back a little bit. If you want to reproduce these observations that I showed you here in the Milky Way, you normally need to account for the whole evolution of the Milky Way with time, because these stars again were created very early on, and so you're not satisfied with just the local measurements. So when you build a complete galaxy evolution model, either semi-analytical, like it's shown in this paper by Cote et al., or a numerical model by Van de Voort et al., what you see is that actually because of the very large delay times between the formation of the neutron stars and their merger, these models, at least, are not able to reproduce the abundances of europium at low metallicity. So this is what is shown, for example, in this upper plot by Cote et al. So the points are exactly the ones that they showed you. And well, here this is a rather simple analytic model where the coalescence time is taken to be 10 mega years with this in this dashed line. And then you're sort of good. But if you push it towards more what is believed to be by some people more realistic delay times, like 30 mega years or even 100 mega years, then obviously you start enriching your galaxy too late. And when you do it a little bit more accurately with this numerical simulation by Van de Voort, they arrived at the same conclusion. So here at the left plot, the black line, which tries to reproduce the abundances with using only neutron star mergers, is not able to catch this higher abundances of R process elements, these red points, for example. And so they postulated that actually what is responsible for these early enrichments are some sort of exotic supernovae, for example, collapsars, and you can also build models where you have this very rapidly rotating collapsing stars, and in this case, they can produce a very large amount of R process elements, sometimes up to 1 solar mass. The rate of these events is very, very low, perhaps a sub% level of core collapse supernovae, but that's okay if they produce a lot of mass per each event. And so there is this other suggestion that actually what the sites that are responsible for our process elements are these collapsed stars, even though what we see in the local universe is, we just saw this one event, the GW 170817. So what is the difficulty in actually modeling all this is that, as you can imagine, on top of the galaxy evolution models that are in the cells complex, you don't need to include, you need to include the binary star formation and merger rates, which are actually not very well known. We have so far, maybe I forgot to mention, there are 2 binary neutron star mergers observed with LIGO and Virgo, one of them with the electromagnetic counterparts and the other one without. So we just have 2 events to measure the local rate. And we have a handful of measurements in the galaxy, but again, we don't know much about the evolution and formation at higher redshifts. So I don't really want to go into the details of these processes, but this cartoon shows the complex path of evolution of binary neutron stars, starting from 2 zero main sequence stars, through the collapse of one star, common envelope evolution, or maybe even 2 phases of common envelope evolution, where one compact object is engulfed in the envelope of the second star, until the collapse of the second star, and finally the merger. And all this process can take a long time, but also contains many unknowns. In particular, the supernova explosion mechanism, this common envelope phase, the birth kicks of the neutron stars that can disrupt the binary or dislocate it. And here I show an example of the work by Santolicchio et al., which shows the merger rate of binary neutron stars as a function of redshift. And the gray box is the constraint from gravitational wave observations. And the different lines correspond to different, just one parameter, this common envelope efficiency parameter. And among many other parameters you can vary. And this model, so this is a population synthesis model that follows the evolution of 2 stars and their interactions. And you can appreciate that even models that are compatible with the local measured rates can have a vastly different merger rates at high redshifts. For example, here between the red line and the yellow line. So there is really a lot of unknowns at high redshift that is going on. A different way to put it is through the delay times from formation and merger. So as I said, most population synthesis models prefer the distribution of delay times of 1/t, which is what is shown on this left-hand side plot. It's maybe not really obvious, but the black line up until this point is basically 1/t. So this is the number of binary neutron stars that merge today. This is the black line as a function of the delay time between formation and merger. But there are claims that actually the delays can be much shorter. For example, in the works by Pais Bignamini, and in this work he looked at galactic binaries, and just by looking at their separations, he inferred the distribution of their expected delay times between formation and merger. Of course, there are just a handful of these systems, about 15, I think, but they imply completely different distributions. So this is the black line, which is the distribution of the delay times for galactic binaries, and it's not compatible at all with the 1/t distribution shown in red. And then there are also some recent suggestions that actually this delay time between formation and merger may depend on the mass of the neutron stars itself. So it's not maybe even really universal. So to explore all of this, we recently looked into this with Frédéric, Elisabeth, Joe, and our collaborator Stéphane Gorelli in Brussels. And this is the work that we're going to continue also for this project that Elisabeth mentioned. And basically, we relied on the galaxy evolution models that were developed by here in IP and in a series of works, which is schematically show here a merger free of dark matter halos, which is the basis of our model. And then we insert gas physics inside each of the halo, and we follow the gas accretion onto the galaxy, cooling, star formation, and etc., all the galactic physics. And we follow the production of elements in stars as well as in mergers, which I will describe, and how these are ejected in the interstellar media and mixed thereafter. So In this work, we focused on the Milky Way-like galaxy to try to reproduce the observation. We looked into the formation and merger rates of binary to star mergers. And in particular, we included formation efficiency dependent on the mass of the progenitor stars, as well as on the metallicity of the progenitor stars. So this evolves with redshift as well. And we looked into different phenomenological models for the distribution of time delays between the formation and the merger, which I show here in this plot. So it's not really crucial for next for what is going to come. But what I wanted to emphasize here is that this plot shows the delay time distribution between formation and merger. So the colored lines are phenomenological models, and the black line is what we obtain from these population synthesis models. But they're not they do not really resolve these very short time delays. So one of the avenues to explore are really short delays, or what they call fast mergers, which obviously are crucial for resolving this issue. So we looked at the range of this delay time distribution models, and I just want to show here the merger rate that we used, that is the outcome of our model versus redshift and stellar mass of the host galaxy. Because this is one point that is different between our model and different works. So the y-axis is the merger rate of the binary neutron stars, and the x-axis is the stellar mass of the galaxy that hosts the merger. The colored points are our model. So each point is basically a galaxy that will later merge to become a Milky Way-like galaxy. Color coded according to the age of this galaxy. So these red points are very early small galaxies, and the lines show the predictions from different population synthesis models. Again, color coding in the same way, and we are sort of consistent with the predictions of these population synthesis models, even though what is crucial here again is the dependence on the merger rate, not only on the redshift, but also on galaxy mass, because at the same redshift, you can have obviously different merger rates, but also at the same mass, you can have this different merger rates. So this will be an important component of the model. And another critical component that we included is the turbulent mixing of these freshly synthesized elements in the interstellar medium. Now, when you create these R-process elements by neutron-star mergers, since these are very rare events, they're not immediately enriched. They don't immediately enrich the entire galaxy. So what we used here is a scheme proposal, a suggestion by Benjamin and Takizaka, but here we implemented in our complete galaxy evolution model, where here, for example, we have the black dots are the sites of the binary neutron-star mergers, and they enrich the immediate surroundings with the R-process elements. And then at some later time t, these elements slightly diffuse, just following this is just the solution of the diffusion equation. So you calculate the density surrounding this merger site as a function of the time that passed since the merger and the location of the merger. And then at some later time, t3, it dispersed a little bit more, but then the density also slightly decreased. So it's really just a solution to the diffusion equation when you have a Gaussian that sort of diffuses, but also the peak declines with time. And then we have the observer stars, so basically just stars that are created at random points in this potential of the galaxy. Of course, if the stars happens to form really close to the merger, both in time and in space, it will be very much enriched by the material, by the R-process material. It will be overabundant in this case. And if it happened to form very far away from the enrichment sites, then it will not be enriched at all. So by this way, we kind of try to account for special effects, even though inherently our semiotic model does not have special resolution, and so these are the results. So we find that our model does reproduce the abundances of R-process elements both in low and high metallicity environments. So in particular, I show you here even at these very low metallicities, -3, again 1/1000th of the solar value. The blue lines show the model mean, and then the dashed lines show the different quantiles of the distribution of the stars in each metallicity bin, and the black shows the mean of the observations. So even at very low metallicities, we do have well, model stars that are very enriched, and the mean follows very well the observations. And even the shape of distribution follows reasonably well, even though it differs slightly at this intermediate metallicity. So there is something to think about. But also the low abundance end, it fits the observed distribution very well. So even though here we took a distribution of delays of 1/t, but there are the effects that we still took a rather low minimal delay, and also this turbulent mixing effect actually causes certain stars to be over-enriched even at very early times. Okay, so this plot will also explore a little bit how it depends on this diffusion coefficient. Of course, if I told you that the turbulent mixing depends on is basically a description of the diffusion of these elements in the interstellar medium, it depends on the diffusion coefficient that we choose. Here, unfortunately, I forgot the units. It's kiloparsec square per gigayear. And we saw an interesting effect that the dispersion is actually not monotonic with the diffusion coefficient. At first, it starts when you go from very low, so diffusion coefficients of blue to red to green. It's actually, it grows with diffusion coefficient. But when you go to huge diffusion coefficients, it declines. The dispersion declines again, because if you have immediate diffusion, then basically everything mixes up and you have zero dispersion. But here, the reason why it's not homogeneous is actually interplay between the timescales of the diffusion and the timescales of mergers between these protogalaxies. Because when two protogalaxies merge, then they merge everything inside. So there is some interplays between the different timescales, which we are now trying to explore further. And indeed, concerning the time delay, so if we compare models with here on the upper plot with the same mean time delay, then we see that this mean time delay actually, well, average delay time, determines the abundances at high metallicities, but it can have large differences at low metallicities. What determines the abundances at low metallicities is the fraction of fast mergers, where fast is below 100 megayear. So models that have the same fraction of these fast mergers have roughly the same abundances at very low metallicities. So this allows us to explore a bit this end, but it really just raised the question of, are these fast mergers actually occurring in nature? And I think the current population studies models, well, they still need to be developed a little bit further to answer this question. So to recap this part, I just told you before that many models do not reach this conclusion, and I showed you this simulation by Van de Voort. So what are the differences between our approach and these other galaxy evolution models? Well, there are a lot of differences, and sometimes it's different to compare because our model is semi-analytic, and these mostly models are numerical. So of course, it'll be interesting to test these new effects that we include with a full numerical model of a Milky Way-like galaxy. But basically, what we use is a neutron star formation and efficiency and binary neutron star merger rate that depends on the local conditions, in particular on the metallicity. So here I show you the merger rate, the merger rate efficiency as a function of the metallicity in the different halos. And what these models typically use is a constant value here. So this is a merger rate per unit of mass formed in stars. So here it's in our model, it's not at all constant. As I showed you before, this prescription allows us actually to be consistent with the predictions of population stasis models. So I think it's important to include this in the models. Now another thing is that we explore a larger range of time delay distributions between formation and merger, and we also include turbulent mixing that really allowed us to enrich these low metallicity environments extremely efficiently with europium. So to conclude this part, I think this is still an open question. So now with again, so with this Belgian project that Elizabeth mentioned, what we're planning to do next is to further explore this, maybe also include collapsars in our models, and explore different formation efficiency of BNS mergers and whether they are compatible with observations. So now let me go to the next part of my talk, and again show you this plot that shows the horizon of gravitational-wave detections as a function of the mass of the binaries. So far I talked about binary neutron stars, which would be somewhere here on the left side of this plot, and I discussed ways to infer or study the effects of these mergers in let's say higher redshifts. But what about all the other solar mass systems? So all of these systems, let's say, that are beyond the horizon of LIGO, Virgo, and Kagra, and are currently not detected and don't have a chance to be detected, but they still merge. So what happens with them? So they merge and they produce a gravitational wave signal. Now the signal from all of this binaries is superposed, and even though we do not resolve each and every of these binaries, there is a huge number of them, and together we believe they produce the stochastic gravitational wave background, which is, I'll show you in the next slide, is really much more faint than the noise of the detector. So it's very, very difficult to detect, and it has not yet been detected. So the stochastic background is actually in some way a window to the high redshift universe that we cannot observe right now. So it can be of astrophysical origin, like I just described, like unresolved binary systems, supernovae, or rotating neutron stars, which has some deformations on them. But they can also be cosmological, and of course, then the signal is truly inherently stochastic, like inflation and cosmic strings and etc. So this there we go to the really very, very early universe, and especially if you go to the lowest frequencies, this is the signal that that we would like to observe with CMB experiments. So this signal can be extremely rich in information, and as I said, it's not yet been detected. On top of exploring the different components that make up the total stochastic gravitational wave background, they can also be anisotropies. For example, for the astrophysical component, just because the host galaxies of these events are inhomogeneously distributed in the universe. So just like we have anisotropies in the infrared background, we expect to have anisotropies in the stochastic background, and this was extensively studied here on IP and in collaboration with Julia Cousine and Cyril Pitrou and Jean-Philippe and myself. And so there's a lot to study there. So here if you assume that the background is from astrophysical origin, the background here in units, so the energy density in units of the critical density of the universe is just the sum of all the contributions from all the mergers. So this is R is the merger rate occurring anywhere in the universe. And if you do a calculation, you see, so this plot is actually slightly outdated because it was based on what we knew back then on the merger rate, which has since then gone down, and the sensitivity of the instruments which actually decreased. But nevertheless, the plot shows the background from black hole binaries that could be detected with LIGO and Virgo here in black, and also with LISA here in the sensitivity in blue. Although on some level, actually, it will be a foreground for the cosmological signal that LISA is after. So both for astrophysical interest and for the hope to detect the cosmological signal, we would like to learn more about the stochastic background. And the ways to, so again, coming back to the redshift dependence, you can study it from both ways. So one would be a sort of model-based approach when you predict the signal based on your preferred astrophysical model. So this is just an example of some model that I just had found on my laptop, and it shows the stochastic background, again, in some units of the critical density of the universe, the total in black, and in different redshift bins in colors. Yeah, you can see that, of course, the contribution from high redshift is subdominant, but it is still there, and you can maybe predict the total signal by looking at the contribution of different redshifts. You can also use a database approach where you come up with a phenomenological model for the redshift distribution of the sources, which is what they did in this paper by Callister et al. And what they did here is they had just some distribution of the merge rate versus redshift. So here in both plots, this is the black line. They input it into the model, produced mock data, and then looked how many merges they actually detected. So of course the detection horizon, as I said, is very close. It's really up to redshift of 2. So it's not surprising that they could not constrain the merge rate beyond this redshift. And so they constrained the 1 sigma, I believe, is this lines, this dashed lines here, and you see that they completely missed the injected signal. However, if you also use the information from the stochastic background, even just the non-detection of the stochastic background, you can constrain the signal much better, which is shown on the right-hand side plot. So how do you detect the signal? So the signal, as I said, so this is really much fainter than the noise. So this is on the upper plot. I showed that this is the signal from the individual sources, but they are all blended up, and the noise on this scale will cover the entire plot. So just all inside the noise. And so what you do is you cross-correlate the outputs of 2 detectors or pairs of detectors, and you hope the noise is uncorrelated with the signal and it's uncorrelated between detectors. And so you can define a correlation statistic here which is the correlation of the outputs between these two signals. Sorry, I see there is some question in the chat, but I cannot really read the chat when I'm talking. If you have questions, please speak up, because
it wasn't a question. I was just warning you about the time.
Oh, can you tell me how much I have?
So it's 11:45. So.
Oh, okay. Thank you. Okay. Oh, I need to speed up. Okay. So we find this correlation statistic. So S are the two signals, and this gamma is a geometrical effect of the detectors, and S is the model for the signal. And the expectation value of the statistic is the stochastic background. However, in reality, the noise is correlated because you have both power in instrumental lines, you have a non-stationary noise in your detectors, and you have what is called Schumann resonances, which are electromagnetic signals that trapped between the surface of the Earth and the ionosphere. So just standing waves that are correlated between over the scale of the entire Earth, so obviously between the detectors as well. And so so this is so I'm a little bit involved in the data analysis for the for LIGO and Virgo data. And so what we do, what is done is you first correlate the outputs of 2 signals, but first you shift them by a large amount, by few seconds, so that you know that if you detect something, this is not the signal. And after you detect all the artifacts in the shifted correlations, and you make sure that you remove all them, or you know their source, and the noise is Gaussian, then you remove the shift, and you open the box, and you see the actual signal, which is shown here for the O2 LIGO run. So this is the correlation statistics, and again, the expectation value is exactly the stochastic background. So you can come up with constraints on the amplitude and the spectral shape of this background. So this is yeah. So this is the constraints from O1 plus O2 LIGO run. So shown here in orange, and the predictions for the stochastic background in violet. So the analysis of the all 3 LIGO Virgo data is finished and will be published very soon, hopefully beginning of January. The good thing about stochastic background is that we know that the SNR grows with observation time. So even though right now the signal is not detected, or maybe predictions are difficult, but we know that the SNR will go with time. So we know it will detect it with LIGO and Virgo. So this is the good thing about it. Okay, so more discoveries to come. And in the last few minutes, although I really, may take slightly more. I want to talk about a different part of this mass redshift plane, which is the larger masses of the massive black hole binaries that hopefully will be detectable with LISA. So really quick, LISA promises us. So this plot is also a bit outdated. It's from the LISA white paper. LISA promises us to detect black holes basically through the entire universe, right? But it also depends on how many black hole binaries are there. So how many will we detect? And here the predictions vary widely. So again, you can explore them with semi-analytic models. And then the predictions are typically more optimistic, between 10 and 100 per year, or with hydrodynamic simulations. And here the predictions are usually more pessimistic, maybe a few per year. So the question is how to, not only how the model is, but we want to know how many sources we will have, and also how to plan the observations. What are the sensitivity regions that are critical to explore this or that scenario? So this is really crucial for preparing for LISA. So just very, very quickly on how massive black hole binaries form. So we talk a little bit about star mass black hole binaries. So massive black hole binaries start with seed black holes, so the small black holes that form very early on in the centers of galaxies, and they grow through accretion in galactic centers. And then, okay, I'm not going to go through maybe all of these stages, but the galaxies merge, so the black holes sort of approach each other, still separated by tens to hundreds of kiloparsec at this point. We then believe that through dynamical friction, they form a bound binary. The orbit then decays through interactions with gas and stars in the center of the galaxy. And finally, they become close enough so that emission of gravitational waves becomes efficient, and they merge. But you can see here in bold how this involves very, very different scales. And indeed, so you can imagine that it's extremely challenging to model such a process, even with hydrodynamical simulations. And so, of course, there are also many unknowns on the way to merger. And so different models obviously differ by how they treat all this all this physics. What I forgot to mention concerning the semi-analytic models and the hydro simulations is that there is an interesting interplay between the two approaches, because often hydrodynamic simulations use so-called subgrid models that are inspired by analytic models or semi-analytic models to describe effects that are not resolved in the hydro simulation, whereas semi-analytic models also use the results from detailed hydro simulation that focused on this or that particular effect. So there is a continuous exchange between the two sets of models. So hopefully we will converge to something in the end. So here I want to briefly mention just some of our recent work on this, which relies on other effects that were studied. In particular, one is the supernova feedback in the centers of galaxies and its effect on the growth of black hole seeds. So this was explored by Johan, Marta, and Melanie in several recent papers. And on this plot, I show the black hole mass versus the stellar mass of the galaxy in two of the simulations that they ran. One with, on the left with, let's say, mild feedback, and on the right with strong feedback. I hope I'm not saying anything stupid. I think Johan is not here to correct me. Hopefully Marta is to correct me. And so what they found is that the feedback from supernova in the galactic center removes gas from the surroundings of the black hole, and it prevents its growth. And you can immediately see it for the galaxies of, let's say, 10 to the 9 solar masses, where with mild feedback, the black holes can grow up to 10 to the 6 by redshift 3, but only 10 to the, let's say, 4 in the case of strong feedback. So you can, if they only grew that much by redshift 3, they will not go much more. Well, I mean, obviously that sets already the scale for the mass that you will observe for the merging of black holes. And another interesting recent result was by Michael Tremmel, where they showed that massive black hole binaries well, even after the galaxies merge, the two black holes not immediately form a bound pair. In fact, it can they maybe never even form a bound pair, even though the host galaxies merge. So this is completely opposite to many assumptions often made in these models, where as soon as the galaxies merge, the black hole sort of merge as well, or at least form a bound pair. In fact, they predicted that many black holes never merge, and they're left wandering in the outskirts of the galaxy. And they did it by carefully taking into account dynamical friction effects of inside the galaxy. And even those black holes that do form pairs. This plot shows, for example, look at the black line here. This is the cumulative fraction of pairs, well, bound pairs, as a function of time. And you can see that only like half of them form a bound pair within 1 giga-year. And most of them take much more than a giga-year to form a pair. So in fact, there is sort of a dissociation between the merger of galaxies and the merger actually of black holes, even the formation of bound pairs. And so all this was included in other, as well as other effects, in the recent work that we did with Enrico Barausa, that I think you all know, Marta, as well as Michael Tremel and Matteo Bonetti from Milano. So this was an extension of previous models that were developed by Enrico over the years. And it's the basis is the same. He uses merger tree of dark matter halos and plants some gas physics inside. So the idea is the same for semi-analytical models. So here we included the supernova feedback as well as this kiloparsec scale wandering, and other effects like a dynamical friction on even smaller scales, quadruple interactions of black holes. So when you have triple black holes or quadruple black holes, etc. And we explored the range set of models. We explored 12 models in total to bracket the model uncertainties. And so the results are in this table. And I guess okay, thank you, Rafael. I'm going to finish quite soon. Sorry about taking too long. So just to highlight the results, so we predicted, even with our most, let's say, pessimistic models, that both prevents the growth of seeds through supernova feedback and includes all the delays that we can think of, predicts about well, a few mergers per year with LISA, which is, I guess, I would say this is sort of in between the predictions I showed you just before. And okay, so since I guess I'm supposed to finish now, I will just flash this slide, where we explored the host galaxies with massive black hole binaries for these different models. Well, this is just a subset of the models, and the take-home message is that first of all, well, the take-home message, I guess, if I don't have a lot of time to discuss it, is that we found that mergers in low mass galaxies actually dominate the total rate. So this can be seen here. So everything that is below 10 to the 9, 10 to the, is basically dominates the total rate. And this explains why some of the numerical models actually underestimate the rate, because they maybe lack the resolution of the dwarf galaxies. And we also found that very long time scales, about giga-years, exist between galaxy merger and the massive black hole binary merger, even among binary black hole mergers that are detected by LISA. So even those that are detected, they are detected by actually the galaxies merged many giga-years ago. And this is consistent with some of the numerical work, even, for example, the recent paper by Marta and collaborators. Since I guess I'm supposed to finish this, I'm just finished with an application for pulsar timing arrays. So while we found that there is a large range of predictions for our models, so again, am I going to this to this table for the rate of mergers detected by LISA? It's a factor of a few between the different models. We also calculated the expected signal for the pulsar timing array experiments, which receive signals from a range of pulsars around Earth, and see if the time is deformed, well, delayed by the presence of a gravitational wave in the vicinity of Earth. And we found that actually, because the PTAs are sensitive to the most massive end of the mass scale of the binaries, in fact, at the most massive end is not really sensitive to all of these physics details that I just described. And actually, all of the models predict more or less the same thing. So this is the colored band for the PTA signal. So these lines are sensitivities of the different PTA arrays, and we're comfortably below the current sensitivities. And of course, the sensitivities will be greatly increased with the SKA. And now, just recently, there was a very intriguing tentative detection of a correlated signal by the Nanograv collaboration. This is an American pulsar timing array experiment. And so they found evidence for a common spectrum process, so something that is common for all the pulsars that they observed, but not the special correlation that is expected from a gravitational wave signal. And moreover, so I showed that this is a star here. It's actually in tension with previous upper limits, but it's very intriguing to see further developments of this tentative detection and whether this is really a signal from gravitational waves, from binary black holes, or some maybe cosmological signal that maybe we've discovered. Okay, so this is really my last slide, I promise. Just to sum up, the future of gravitational astronomy looks bright. There are upcoming observations with LIGO, Virgo, and Kagra scheduled in 2022. Well, of course, delayed because of COVID. Pulsar timing arrays, as I said, is an ongoing effort. So maybe discoveries are just around the corner there. And of course, LISA is scheduled for 2034. And besides massive black holes, there's a lot more to discover with LISA. Extreme acceleration spirals, cosmological signals, white dwarf in the galaxy, really a host of signals. And finally, there are third generation detectors like Einstein Telescope and Cosmic Explorer that will allow us to really observe these stellar mass objects to much higher distances. And looking even further into the future, there is, as you know, there was this process of Voyage 2050 by ESA, looking into the missions to for the year 2050. There were, I think, 5 gravitational wave projects submitted, most of them developed inside the LISA consortium, including our project about high angular resolution gravitational wave astronomy. So that was a fun thing to think about. We wanted to send 2 sort of LISA-like satellites to allow for high angular resolution astronomy, but we'll see what comes out of it. And obviously, we're all waiting for more electromagnetic counterparts for all of these events. And finally, I want to wish you happy holidays, and I hope to see you very soon in IP. Thank you.
Thank you very much. Thank you very much, Irina, for this excellent talk. Raphael, we can have many questions.
Yes, so we're gonna take questions. So I haven't, you can unmute yourself, go smoothly, and take the speech if you want to ask your question.
Okay, some question?
Yes, I have a question.
Yeah?
Joe here. You argued that, that was a very nice talk, thank you. You argued that massive black hole mergers might be dominated by smaller galaxies. What is the effect of AGN disks? Would that not enhance rates for more massive galaxies?
Well, we did not include that. Wait, AGN. So could you be more specific?
AGN accretion disks, you know, are an environment where one could have enhanced mergers of massive black holes.
So here we did not really looked into the details of the disks. No, but. Yeah, yeah. I don't know how to answer the question. We did not look into this, but in general, it would. You mean the intermediate mass black holes?
For example, yes, or even more massive ones. I mean, you would get more dramatic dynamical friction effects, maybe.
Yes, that's right. So it depends on how you see them. In here, we assume that they are all. Just seated in the peaks of the density distributions, but you can certainly imagine a scenario where they are born in the galactic, well, in the accretion disks. and then grow there. This is this was actually discussed in some recent papers. I forgot the first author, but
by Hyman basically and his collaborators, I think.
Yeah. There were also other papers. Yes.
Yeah.
But then this would require a completely different channel of forming the black holes. So that will be another argument in favor of these dwarf galaxies as being the main host of black holes. Yes.
Thank you. Other question?
So yeah, I think I will take. There are two questions. But perhaps we will take them in order as they arrive. So Gary first.
Hey, thank you, Irina. That was a great presentation. I learned a lot. Finally, I'm amazed at how one can make predictions given all these uncertainties. For example, for me, the huge uncertainty is just at the small scale level, the LIGO scale, is the binary formation. Okay, and whether it is in the field or in globular clusters will make a big difference. And all this for me is still very murky. But my question is regarding the data of European, so the R process elements, abundance to iron versus metal abundance. I was wondering if you could improve your models by adding other chemistry, for example, maybe alpha over Fe or something like that. Could the models make different predictions, and then you can just compare it to the data, which give you an extra dimension?
Yes, so thanks for this question. That's a very good point. So we did compare with alpha over Fe. So our models are, the basis is that the alpha over Fe is compatible observations. I don't have a slide here, but so here we go. But it's going to look at different elements, because what you could look at is radioactive elements. So radioactive R process elements, like the ones shown here. This is one of the things that we want to look into a bit more with our model, because if you have radioactive elements, that essentially gives you another time scale that maybe can break the degeneracy. So if you observe a radioactive element, that means that not more than a few times times have elapsed. So definitely looking in more elements will have to break the degeneracy.
Okay, great. Thank you. Yeah, of course. So that's even better. And then I had a little comment, since I have the microphone. You mentioned that there's only one kilonova event known, but in the figure you showed at the very beginning, the first figure, I noticed two. So did I miss something?
You mean which figure? The very first one?
The very first figure, this one. Yeah, there seems to be two neutron star mergers in this plot.
Yes, exactly. There are two neutron star mergers, but one of them, well, this one does not have an electromagnetic counterpart.
Do we understand why?
Yes, it was too faint. It was really too far away. So
okay. Interesting. Yeah, because of course.
We expect most of them will not have electromagnetic counterparts. Actually, that's
because the signal, the electromagnetic signal scales as 1 over distance squared, in contrast with the gravitational wave signal, which goes as 1 over distance, right? Like
exactly. That. Yeah.
Okay. Thank you very much.
And also the localization of most of them is not sufficient to quickly find them.
Okay. All right. Thank you very much, Irina.
Thank you. And also for the predictions, I'm not getting fined if I make the wrong prediction. Like you.
Okay. So let's move on. Next question. So you go first.
Hello. So I actually had the exact same question as Gary about European over Aaron, but I have another question. So in your slide where you were showing your different model, I think it was slide 16. You're showing the different models and proving that you are recovering the scatter of the data. But clearly you see that in your model, this one for instance, in your model, so you reproduce the scatter, but the mean when you change the model varies. So I was just wondering, can you give some constraints looking at the mean, comparing with the mean of the data?
Yes, certainly. So I guess in this plot, I show the mean of the data, which is in black, and the mean of the model, which is in blue. So for this this is the, I guess, the fiducial model, which is chosen so that the means fit and well, sort of the scatter, well, the dispersion. But eventually what we want is exactly that, like you suggest, is to fit both the mean and also the shape of the distribution by varying the parameters, which are so the method here is to fix most of the galaxy evolution models as much as we can by using, for example, like Gary suggested, the alpha over iron and the star formation rate and all that, and then fit the binary to star merger parameters like the delay time distribution, I don't know, the fraction of mergers, etc., to fit this. So this is eventually what we would like to do, but we're not there yet.
But in your following slide, I mean, the mean clearly differ between one model and, no, yeah, this one, for instance, in bottom right. The mean clearly differ between one model and the other. So can you exclude some model already with this?
I wouldn't say that I can exclude it because for this you would, yeah, well, so they differ. So yeah, I would say that this orange model is maybe less likely. It's really far away from what, even by eye, it's really far away from the mean. So I guess some models can be excluded. Here it was more of an exploratory work to see the effects of the different parameters that we have. So I would say that, yeah, some models can be clearly excluded. For example, here it's, and here it's much lower because, for example, this orange model, because the, well, anyway, because of the shape of the distribution of time delays, and it's, but you can exclude some models, but I think you would need a better understanding also of the selection effects of the observations relative to how we model observations in the simulation. So for the results that I have now, I wouldn't really exclude a lot of models other than really the most extreme ones like the one I showed here. But I guess, yeah, the idea is to exclude models if they're far away from the, yeah, from the mean, obviously.
Okay, thank you.
Okay, Nikos, you had a question, it seems, or at least you are muted.
Yeah, I also thank you very much, Irina, for this very nice talk. I really enjoyed it a lot. I come back also to this problem of europium at high metallicity now. As you, I don't know if you said it, the problem there comes from the fact that in those high metallicities, both iron and europium may come from the same, from sources which have the same distribution of delay times. Specifically, iron comes from type 1a supernova, which have a delay time distribution proportional to T to the -1. And if we assume that europium comes from neutron star mergers, they also have a delay time distribution proportional to T to the -1. So the two have the same dependence on time, and so their ratio should remain constant. This is the problem that most people have with that. And now in your case, I'm not sure I understand how you solve that, making europium at lame times with respect to iron going down. Could you explain that a little bit more? It's not clear at all to me.
Yes, so this is something that yeah, we showed in this work, but this is something that I really want to look into a bit further because initially it was not our focus. Initially we were focusing more on the low metallicity side, and then we found out that we kind of also reproduced the high metallicity side. So indeed, starting from about this metallicity of this -1, you would yeah, most models have this flat behavior here, and in this well, the behavior that I obtained here is actually it's very much dependent on the star formation rate at late times here.
I'm not sure. Both of them depend in the same way. Both neutron star mergers and the type 1a supernova, they're binary systems. If they have the same delay time distribution, at late times they behave the same way, their rates.
That's true, but still I still have some, well, the delay times are sort of the same, but they're not identical. Just the distribution, the phenomenological form distribution is similar. For example, like here, but the other parameters of the formation are not the same, and in particular, what is not the same is also how they are produced. Because for the iron, I assume that it's produced and immediately dispersed in the interstellar medium. So I don't have all of this detailed description of the dispersion, because there are so many of the supernovae 1A or even 1A. There is a lot of them. So this and this is actually another. So for example, for the model without the turbulent mixing, we also got a flattening here towards high metallicities. And so the fact that we include this sort of kind of special resolution just for the BNS mergers actually made this and the declining star formation rate is what made this decline at high redshift, at the higher metallicities.
Thank you, Irina. More questions? Raphael?
Yes, can I ask a question on this same plot, and this time at intermediate metallicities? I'm wondering why the 95% quantiles are so different from your model and the observations, in the sense that this model allows to reproduce the scatter, which we observe at lower metallicities, and then afterwards it converges correctly, as Nikos discussed. However, in the intermediate, it seems that the scatter is overestimated. Is it, or?
Yeah, it seems that the scatter is overestimated. That's true. So this is, yeah, I mean, well, that's what the model predicts. So the question is there something that is, so you can observe, if you look at the data, that the scatter is, if you try to look at the black lines that are a little bit difficult to see, their scatter is huge at low metallicities, and then it becomes smaller. So there is a critical metallicity where the scatter becomes smaller, at least what you see in observations. So the question is, what is this scale connected to? Can we, is there something, maybe some effect that we actually don't take into account here? So this is one of the possibly ways to see the transition between the low and high metallicities. But well, the model says what it is. And one of the ways is really, but as I said before, it's like the next step is to try to fit the entire observed distribution really with details. Here we were really already satisfied with fitting the mean, but we have to look after some processes that perhaps occur at this critical metallicity. Maybe, like I said, there is, so the mixing timescales play some role. So we need to maybe adjust the mixing or include a different way mixing by the galaxies, because for now, for example, I assume that each time the galaxies merge, everything inside is completely mixed, but that is clearly not the case. So some of the timescales that are in my model actually not well, they're not correct. Well, there's an approximation.
And I had just another small question.
Yeah.
I have no idea how these observations are really done, but is it possible that there can be also selection effects here, by which stars at large metallicities, it can be difficult to distinguish the European lines or things like that? Or should we really rely on, I mean, firmly on this data and on the positions of these stars in this plane? So
in this range, well, I'm not, as you know, I'm not really an expert on observations at all. But as far as I understand, in this range, there's not supposed to be selection effects that are very important. At the high europium enrichment levels, you would just have very defined lines, and the lower end it starts being unresolved, but it's below the abundances that are shown here. So this range, we should be okay, but of course there is some stochasticity just in the sense that, well, you happen to observe this star is not the other one,
right?
The star here, I don't know.
But nothing intrinsic. Okay.
Thank you.
Yeah.
More question?
Thanks.
More question? Raphael, no?
No, I don't see any more people willing to ask questions. So,
okay.
So perhaps we can stop now. So,
Yeah.
But before, we can thank again Irina for a nice talk.
Thank you very much.
Thank you everybody for connecting today.
So, well, we can keep the conversation open for a little while, a little longer. There are more specific questions as people slowly quit. And in the meantime, I wish you all the best for the end of the year.
Yes, thank you very much, and all the best for you. All the best for you. Happy holidays. I hope you can find a way to spend them with your families and.
Yeah, thank you to you, and happy Christmas. Goodbye.
Bye, everyone.
Irina, if I can ask another question.
Yeah, sure.
So what is your take on the origin of the black hole events that that are seen by LIGO? Do you think it's mainly in the field or mainly in globular clusters?
So I think, okay, but this is, you know, my take. I don't know. My personal opinion is that, for example, the last one.
You can reply off the record if you want. I can stop recording.
Yeah, maybe. Well, maybe. Well, shouldn't you stop the recording? So I think that, for example, the event, you know, in the mass gap, it has to be in, well, obviously has to be in globular cluster. Even though there were some works that recently that show that in fact the mass gap itself is very, very uncertain. It can be uncertain by 10, 15 solar masses. But I think it's plausible that the globular cluster channel has some contribution, and this mass gap event is a great candidate for that, I think.
So these are the higher mass events, above 50 solar masses, right?
Yeah, yeah. Yeah, they're both, at least one of them is clearly above 60. Yeah, even though the mass gap, yeah, it's not certain, but I think it's, but yeah, I don't have a more based opinion, like fact-based opinion or something. But
I don't know if you saw, we came up with an article with my student Eduardo Vitral, where we did a dynamical analysis of a nearby globular cluster using HST and Gaia proper motions. And we think we were able to detect an invisible dark component, which was very small, okay, in size, which was 1/60th of the stellar size of the distribution of stars. And we argue that it's mainly black holes, stellar black holes. So this could give us some constraints. The size of this distribution can give us some constraints on the black hole merger rates from random encounters. And, but I'm not very good at this, but I think, I was wondering if this could help.
Yes, this would certainly help. Yeah, I saw the paper. I didn't read the paper. I just read the abstract, like most papers. But so yeah, but that'll be an interesting point to discuss. If you have the rate of this black holes in.
We just have a density. We can predict a density profile.
Okay. Okay.
A number density profile for the black holes.
Okay, well, that's already something. Yeah, then it's easy to calculate.
It's really a mass density profile. Okay, so then you have to decide what their black hole masses are. But you know, we could say on average there may be 20 solar masses. I don't know, and yeah. And then you can work it out from there. And then of course, you know, this doesn't tell us if they're in binaries or whatever.